So it's like a real class today. I have students in the classroom and they're talking to each other, and I've got a special guest in a bag waiting to be revealed. I wonder who it could possibly be. And here we are in section 5.3. Hope you can see that. It's cut right off at the top there. Section 5, chapter 5, section 3, Hamiltonian systems. Good news for you. You don't have to have it memorized. When we have the test on chapter 5, it'll be open book, open notes, because you're at home anyway. But I always have an open book, open notes, and you will see why. You will see why that's the case, because there's a little check we got to do. We got to check a couple partial derivatives, and if they differ by a minus sign, then Hamiltonian system methods apply. Oh, hello! And if they apply, then we'll do everything that's on the board. But in 5.4, we study a system where the check is f sub y has to equal g sub x without a minus sign. How are you going to keep track of this? It's just different partials, and one of them gets a minus sign, one of them doesn't. Oh, God, nightmare. So you don't have to have it memorized, but you got to watch to see what's going on with this. And after we do 5.4, we'll do an example where you don't know going in whether it's Hamiltonian or the other one, which we'll see. Oh, hello, it's my weasel. So let's meet our special guest star. It's Coco Bananas, who's still alive. She hasn't had any trouble yet. Say hi, Coco. Oh, you're meeting the rest of the class. Yes. Well, let's get the rest of the class dismissed, and let's pay attention to what's going on here. And here's what's going on. Oh, such a good weasel. All right, so here's what you're given. They won't label this little f or that little g, but the book is going to refer to them as such things. What's given is a derivative with respect to derivative of x with respect to t, derivative of y with respect to t, the usual 2x2 system. But like in this case, it's a linear system actually. But anyway, we're going to solve it using the Hamiltonian method. It gives us some structure and some things that we don't get otherwise. It'd be kind of interesting to look and see that the solution curves that we would get are going to be relatives of what we would get from this system. We can look at that when we're done, because this is a chapter 3 problem, chapter 2 problem. It's just not a toughie, but Hamiltonian applies, because here's the check: the partial of f with respect to x is 0. The partial of g with respect to y is 0. So that's the partial of g with respect to y, but negative 0 happens to be the same as 0. So you have the partial of f with respect to x equals the negative partial of g with respect to y. So Hamiltonian methods work. Yay! Oh, she's a weasel. And she's going to say goodbye to you guys. She's going to say goodbye. Bye. Oh, my weasel's keeping me sane. Okay, so here's what you have to do when the check happens. So this is the check. It works. It means that there exists a function of x and y that we can find, and the level curves of that function are solution curves. So let's see the whole story here. So you get two different integrals. You do the integral of the first thing with respect to y. This is in the book, but write it in your notes as well so you can find it. And then because this is a derivative with respect to y, it's as if you're finding what the y stuff could have been. The stuff that gives you these two equations, what y stuff would you have to get the derivative of x with respect to t being negative 6y? So what would you have to have? Well, one of the things you'd have to have is this. But there could be a pure x term, because if you took the derivative with respect to x, any pure x terms would be 0. Same thing down here. When I do the dx, any pure y terms would have gone to 0. And notice it's at h equals. So these two things have to give the same answer, but you have these two adjusters. You have these two pieces that you adjust with. All right, well, let's do this top integral. I'm going to just continue as if I'm doing these two together down here. So this top one just becomes negative 3y squared plus a pure x piece that I'm going to pretend I don't know what it is. And that's what my h has to be equal to. And my h also has to be equal to, this thing will be a negative x squared, because I integrate, raise the power by 1, divide by the new power, plus a pure y piece. And you can see what h has to be. The pure x piece must be negative x squared. The pure y piece must be negative 3y squared. So I get that my h is equal to a negative 3y squared minus x squared plus c. And we would need h of, say, 0, 0 or something equals some constant. We'd have to have this. We'd have to have further piece of information to find what that c is. But the c doesn't matter. It turns out that the level curves don't depend on the constant. So let's think about this thing. Let's say c is 9. I'm going to erase over here. I'm just picking 9 out of thin air because it's positive. And if I have h of xy equals 9 minus 3y squared minus x squared, then the surface, if you remember your Calc 3, this surface is a paraboloid with an elliptical cross-section. And the z-axis comes down here, and there's the y, and there's the x, and this comes out to 3, and this comes out to square root of 3. That's what the surface looks like. It looks like a helmet. It looks like a helmet, that's not in the round. This guy's not in the round. If you notice, it's longer this way than it is this way. So what are the level curves of something like that? Well, the level curves are these guys. You make a slice, and you get these oblong things called ellipses. And those are the level curves. The level curves are ellipses. Oh, okay. Well, there's a couple of ways we can actually check that. Level curves. Well, let's put it up here. Level curves are ellipses. All right, so how can we check to see if that actually works? Well, because this thing is so simple, we could have done this as a system. We could have done this as a matrix that looks like this. It would have been a negative 6 here, a 2 here, a 0 here, and a 0 here. And that would give me my lambda, my eigenvalue would be the square root of negative 12. So I'm going to get a negative inside of a square root for an eigenvalue, which means my solution curves are either circles or ellipses. And in this case, they turn out to be ellipses. So I can check that's the nature of it. Or there's another way to check. And it's the world's weirdest check. We're going to take a look at the world's weirdest check. This is so oddball. You can't believe it. It's almost like detective work. It's like friggin' Angela Lansbury in Murder, She Wrote. You got to follow the clues. It's not an obvious check. So if we have h equals 9 minus, it was 9 minus 3 y squared minus x squared, and we want to check to see if this works. We could say, okay, we get, we're going to hit this with the derivative with respect to t operator. And we get that the derivative of h with respect to t is equal to 0. Oh, sorry. You take this thing, take that 9 equals this. So you take the equation and you pretend h of xy is 0. So you can take a different level curve. Each level curve has a different value for h. You take a constant value for h. I'm taking h equals 0. But h equals any number will work. You'll still get you'll get a different constant here, but that doesn't matter. When you take the derivative with respect to t, this thing goes to 0. So the constant term doesn't matter. So I get a 0 equals 6y dy dt plus 2x dx dt. So I got to use chain rule for that thing. So in solving this thing, you can bring the 2x over here. So I have a negative 2x dx dt. And honest to God, that's your extra minus sign. It's working in the background. This thing equals 6y dy dt. So you can make the following. I can divide by the negative 2. I can divide by the let's just divide. Well, let's just leave it like this for a second. What we have is we happen to know two things. We have dx dt equals negative 6y, dy dt equals 2x. We're trying to see if this relationship fits this relationship. So what you can do is you can take dy dt and replace it by 2x. And if you do that, this is a 2x here. It says dy dt is 2x. I have a 6y times 2x. Does that equal negative 2x dx dt? And if I do that, I divide by 2x, and these guys cancel, and I have dx dt. That extra minus sign here, let's move it over here, equals negative 6y, which I have. Dx dt equals negative 6y. And the other substitution works. If I had put in the negative 6y here, I would have gotten dy dt is 2x over here. So give me the one, the other one checks. So it's kind of a weird check, because what I'd like to have is an explicit function with all the function of t's laid out so I can take the derivatives directly. But I don't get that. I mean, if you look at it, the derivatives are all with respect to t, and there is no t anywhere in the problem. So you can't take direct derivatives and plug them in. You got to do these little chain rule derivatives. But I do get back, you know, if I assume this, I get that. If I assume this, I get that. So the solution for any constant over here, any constant, this thing works. So that's the other way you can check. Isn't that weird? Totally strange. We'll try some problems. You'll see the assignments on the email and the attached PDF. I'll check you out later.